Let's see. Thank you. Good morning, everyone. Is the mic working? Yes, looks like. It's an immense pleasure to be here and to talk about some of the Android security we've been doing and we've been looking at. Quick show of hand. Who's using iPhones? Okay. Who's using Androids? Nice. I would say about 65%, which is a bit higher than the 50-50 split usually in Switzerland. What do you guess is the overall split across the world? 50-50 like in Switzerland? Higher? So Android is the most dominantly used mobile platform. There's over 3 billion users across 190 countries and almost 3/4 of the market share for mobile phones. There's 2.6 million apps in the App Store and 1.5 billion devices sold per year. We started a couple of years ago exploring this ecosystem and wondered what the security of this ecosystem actually is and how well it is tested, how well it is protected against different sets of attacks. And we started by kind of measuring the whole attack surface, the whole threat and attack space. We downloaded a bunch of system images and we ended up with like 7-8 terabytes of firmware images for different mobile phones and around 11 terabytes of apps. Right, so it's quite a bit of storage that we need for our analysis, and we kind of established a way how to assess the security standards and the security issues on these different platforms. And I'm going to take you a bit on a journey on security and insecurity of the Android ecosystem. If you're looking at the Android architecture, I'm having a bit of an overview. There's different parts in a phone. Like not all parts in a phone are created equal. There's one part where we're running the apps, like these are your regular apps that you're usually interacting with, like Google Pay, Netflix, WhatsApp, Duolingo if you're learning French like me, right? And a bunch of other apps that you're going to be using on a daily basis. Then there's also this trust zone kind of thing on the side, which runs a different set of apps. Right, and here that's part of the security design of the Android ecosystem. There's a whole bunch of apps that are like where the goal is to protect your sensitive data against an adversary that takes control of the native side of the insecure side of the normal world. And things like your fingerprints, your private keys, your any kind of sensitive information is being stored in trusted applications in the trust zone world. And there's some interaction between the two things that are happening, between the two worlds, between the normal world and the trusted world. Right? There can be different attackers. Well, an attacker may be able to install a malicious app and take control over this app, right? And if you see recent news, there's a bunch of cases where apps actually have gone evil after an update. The app itself can be buggy, right? The app can have bugs that could be exploited by an attacker that gain control over the app there. But we could also have bugs in the trusted applications running in the secure world or anywhere in the operating system layer or in the runtime layer that is connecting the two sites. So as I'm a huge nerd, I want to take you a bit on a journey, and we're going to venture into Middle Earth for a while and explore a couple of interesting spaces here. Who has watched the original movies? Yeah, I'm getting too old. For those that haven't watched the original movies, they hold up quite well and are much better than The Hobbit. So we're going to start in the Shire, where things are rosy, everything is good and well, and we're going to cheese some Android applications and figure out how we can easily exploit them. Right? Everything is nice and well, but then we're going to go through the mines of Moria, fight the Balrog, and see what happens or what we can find at the lowest layer of the system. We're gonna get some lembas as a nurture for our long journey, explore Gondor, and finally play with the Palantir and explore different angles of communication. Now let's see and start with cheesing Android trusted applications. So Android trusted applications, these are the most secure applications that hold our most dear data. How can we actually exploit this ecosystem, and how can we find issues and vulnerabilities in this ecosystem in the easiest possible way. Now, if you look at trusted applications, how it usually happens is we've got this trusted application here that's signed in the normal world that is then being loaded into the secure world, right? So given the signature, the secure world actually verifies that the trusted application is fine, can be loaded, and everything is good. So even if the normal world is compromised, the trusted application can be loaded into the secure world. Now, we don't trust the normal world, right? Now, if the trusted application is buggy, we obviously need to update it, right? Now we have the buggy version of the trusted application that is signed, and the new version of the trusted application that is also signed. And there's nothing that necessarily stops the adversary from loading the old buggy version and then exploit this buggy version. An adversary may even, and I'm looking at Samsung here, look across different models and grab a buggy version from one model and then load it on another model because it's signed using the same key, right? So there's an interesting way how attackers can move trusted applications and load trusted applications and then exploit the bugs that are in there. Now, how would you, in theory, solve this? Any idea? Model-specific signature, yes, that's one part. And in addition? Rollback counters, yes, exactly. You need rollback counters. So in addition to the signature, you need a counter that says, hey, I've increased the counter, and I'm only allowed to load the app with the most recent version for the current model, right? And this would prohibit the attacker from loading the old version into the system and thereby protect against these rollback attacks. Now, what we did is we downloaded all the firmware images, analyzed the different apps. We looked at 5 OEMs that together are around 65% of the market shares over the last 4 years. We downloaded all the firmware from these OEMs, grouped phones by OEMs, picked 2 phones per group, and then looked at the different systems, extracted all the TAs from the firmware images, discovered 35,000 TAs across 4 different TE implementations, and then established how well rollback counters were actually increased, or if they were consistently increased, and then also discovered that there were around 8% vulnerable TAs where the rollback counter is actually not correctly increased. So this gives you for free different kind of rollback attack opportunities where you can exploit old vulnerabilities on these systems. Now, as we discovered, this TA rollback prevention is incomplete with very questionable TA vulnerability practices where vendors, sometimes they fix bugs on one model and then forget to fix them on the 20 other models. So usually on the S model, things are fixed, and on the A models that are much more popular, things are not fixed. Because the teams are different and they don't talk to each other. And who would want to actually have a common source base where you can synchronize patches for security vulnerabilities, right? It's way too much work, right? It's way too hard to actually ensure that these systems are correctly patched, right? We also discovered that some of the TAs were internally patched without any kind of disclosure, without any kind of rollback prevention, which is also kind of severe, right? So if a team patches a security vulnerability internally, does not increase the rollback counter, then an adversary who discovers this vulnerability can just use the old version and upload it again, right? And then exploit it on the system. And as I said, security patches are often limited to one product and not shared across the different targets. So there's kind of a lack of transparency regarding this rollback prevention, and we call on the vendors to actually push the security on trusted applications to ensure that, hey, at least we track the different trusted applications and we can test the security aspects of those. In addition to that, we did some fuzzing on these trusted applications by analyzing the different consumers, how the normal world was interacting with the trusted world, created custom fuzzers. You all know fuzzing, I assume. Did some recording on the interaction profiles of the benign applications, and then used this as fuzzing seed for the fuzzing engine to then target trusted application on custom off-the-shelf Android devices. And we also found a bunch of bugs in there. I'm not going to go too much into detail. At the bottom, you always see the references if you want to read the paper or check out the source code. I think the point that I want to make here for this first part of the talk is if you want to exploit Android trusted applications, no need to do fancy reverse engineering, no need to do fancy analysis. Just keep track of the trusted application, build yourself a data set, do some diffing, and you get your nice set of O days or 1 days that are silently patched that you can exploit at any point in time. So far so good, right? So this was the easy part. Let's now go a bit deeper. What's the most trusted component in an Android system? If you go really, really deep into a system, like what aspect do you really rely on to have very strong security property? The secure monitor, right? And we wondered, right? We're always using the secure monitor to switch between the normal world and the secure world. And it's just assumed to be secure. But is it? And we then started to explore this a bit using Elixir. So there's again the normal world and the secure world. And usually when we call into trusted applications, we go through a secure monitor call. And in this work, we actually wondered, are there bugs at this level? Right? Are there vulnerabilities in the secure monitor? And this would essentially mean that you compromise the most trusted component of all Android devices, which gives you immediate access to both the normal world and the secure world. So if you have code execution in the secure monitor, it's game over on any Android devices. We built a fuzzing platform that kind of gets across different kind of challenges, such as figuring out peripherals, figuring out the individual details of the runtime system by doing a snapshot, and then creating good fuzzing harnesses. I'm not going to go into detail for this talk here, but I encourage you to head to Marcel's talk in Auditorium C for all the details on this talk, including a walk through the different vulnerabilities he discovered later today in Auditorium C. So, as we found out, when you dig really, really deep, there's interesting things that you uncover that may compromise the state of security of all the devices. So far so good, right? We've had our easy applications to exploit. We've had our most trusted layers that can be attacked. Let's look at how we can actually communicate, right? How do we communicate with these trusted applications? What's the API? Are there any issues in this API that is being used? And we explored the global platform API to understand how the interaction between trusted applications and the normal world was actually happening, and to ensure that, hey, this is actually secure, this is actually used in a safe way. So again, the same system. We've got the normal world that we assume to be compromised, right? An attacker that has control over an app. And through the secure monitor, they can interact with trusted applications by executing calls into the trusted world. And now we wonder, are there bugs in these trusted applications? And as I mentioned before, we fuzzed these trusted applications using a custom fuzzing framework. But that's way too hard, right? It takes way too much time, way too much effort to actually build a fuzzing harness. And what we observed a bit later on is that, hey, all these applications, all these trusted applications actually follow this TEE, Trusted Execution Environment Internal Core API, which is think of it as a calling convention, how you pass information into the trusted world. And if you don't want to read The Lord of the Rings, You can read the global platform API. It's much better to fall asleep. A couple of thousand pages of API specification, almost as fun as the Bluetooth specification, where I could give another talk about different kind of implementation issues. But this global platform API kind of defines how you interact. And what we have to be aware of, that this is a trust barrier, right? So you're going from the normal world where everything is untrusted to the secure world where the runtime system kind of vets some aspect of the data that is being sent and then verifies and runs, interacts with the trusted applications. Now, unfortunately, the developers that are writing these trusted applications are not always aware of this security boundary. And they may naively trust that the application is just sending some benign information. It's as if you're letting an application developer write Linux kernel modules, right? It may not be the best idea because you're actually crossing a trust barrier. It's as if you're going from user space to kernel space, but here you're going from the normal world to the trusted world where you're running all your trusted application with access to your most sensitive data. So let's have a look at how we can invoke like a feature or a function. Think of it as a system call in the trusted application, and it goes through a common entry point, right? And the function signature is fairly straightforward. There's a session state that is under the control of the runtime system. So this is controlled by the secure world, right? So this is vetted, and then there's an unverified command handler that's coming from user space. Parameter types, and 4 TE parameters. And now for the parameter types, right, the global platform API defined that you can either send data in, copy data out, or actually pass memrefs. Amazing, right? And the parameter type actually looks a bit like this. And if you are in security or have reviewed code, if you're looking at this type def, you should be scared. Because at the same time, we have a union between a struct that contains a pointer and a struct that contains 2 integers. And the parameter types are controlled by the attacker. Now, the runtime system, what the runtime system does is if the attacker defines that the parameter type is a memref, then it will ensure that the mapping between the 2 address spaces is set up correctly, right? So and it will check that the pointer that is being passed in the parameter types is a correct and valid pointer. Okay. Now, if the attacker says, hey, this is just a regular value, it's just an integer, then the runtime system will do nothing. Right? This is obviously fine. Now, luckily, what we have here, we have a recommended type check. That in your function, as the programmer, you are responsible to check that the parameter is actually the correct set of parameters that you expect. So if you want to deref in your code the buffer and access the buffer, then you must check that the parameter type is actually a buffer to ensure that the runtime system correctly set up the mapping. And then you can use the different pointers and copy data in, copy data out, and do all the funky stuff. Now, if you carefully study the global platform API specification, you'll learn that this is optional. So, which actually means that an attacker may be able to pass an argument as an integer type that is then used by your application, by the trusted application, as a memref, which gives you immediate arbitrary read and arbitrary write in trusted applications. And this is an amazing feature for an attacker, but likely not intended by the application developer. And this is an inherent weakness of the underlying API and API design, right? So there's a weakness of the global platform API. This should not be optional. Like this type check should not be optional. And the type check should actually be done by the runtime system when the mapping is being done, right? To validate the arguments. Any sane kernel or sensitive environment checks the parameters before it calls into untrusted or less trusted code. Of course, the application developers who were developing trusted applications were not aware of, hey, I need, like, the standard says it's optional. Why should I check, right? For all the tests that I wrote, this was fine, right? And if they don't have a security mindset, this can turn out bad. So what did we do? We wrote a quick Ghidra plugin that does some binary analysis on the different trusted applications. We disassemble all the trusted applications and check the value flow of this information to figure out if there's any kind of missing type checks in these trusted applications. And we found a bunch of violations that we then reported and got fixed in the meantime. Let's walk through an example, right? We've got this vulnerable function here. There's the TA invoke command entry point at the bottom. The parameters that are being passed here that flow through the application are being used in the vulnerable function. We've got the parameter types here that are being passed along, not used, not checked, but this is obviously not interesting. Right? Now, in another piece of code, another piece of example code to go through this again, we have the parameters that are being passed to the vulnerable function. Here, it's being used as a memref.buffer, which is actually derefed. And we've got the parameter types that are being passed, again, not used. And here, again, the parameter types are not checked by the trusted application. But this is interesting because this gives us a primitive as the attacker. The adversary may mark the parameter a simple type value input because they can, right? They have control over that. The runtime system does not validate the buffer address because it's just an integer, right? It's looking at the int. And then the TA code just accesses it and you have your nice exploit primitive for you to use. We looked at around 6,900 TAs that are global platform compliant, around 131 unique trusted applications that we discovered. So there's a bunch of different versions that are already out there. By the way, if you want access to the data set, you may want to talk to us. We can share this privately. There's 850 vulnerable trusted applications that we found. 33 unique vulnerable trusted applications that had these vulnerabilities in there. 9 of them were publicly known. 10 were silently patched, right? Remember what I said earlier about the vendors silently patching and updating the trusted applications without increasing the rollback counter? That may have happened here, right? So vendors sometimes silently patch without actually increasing rollback counters or actually releasing a statement, which kind of leaves this vulnerability open until somebody just abuses it and rolls back the trusted application and then runs it. We've got a bunch of CVEs and some bug bounty, including some very tedious discussions with vendors that were a bit annoying. Now, we obviously were looking at mitigations as well. So our goal was to actually change the underlying API. So instead of doing a fail open, a fail close design, that the runtime system actually has the means to check the underlying parameters and ensure that the type check is mandatory. We sent the proposal to global platform, and there's a draft for the API update in progress. Now, we published a paper and called it Global Confusion, and they were a bit pissed afterwards from the name. So we hope that our proposal still goes through, and we can make sure that the API is safe going forward. Everything we did is, of course, open source. You can play with it and then use it in your upcoming Android builds. So we're working on safer standards, and we're working with the different platform providers on that. Cool. So this concludes the third part of the talk. Trusted applications look fairly bleak, right? The whole underground, the whole dirty plumbing of the secure world is kind of not so great, right? So let's look at the Android user space, right? And let's see how Android user space fares. And obviously there's tons of libraries out there that are used in all the different applications. There's no sane way of deploying libraries on Android. If you have like native code, every app ships with its own copy of the native code. How do we mitigate issues in native code? Because they are never updated, right? So we have to develop strong mitigations, and Google's answer was to just slap a secure allocator on it. And they developed Scudo for this. So Scudo is a hardened memory allocator that tries to protect against all the different kinds of heap corruptions. So it's a user-space memory allocator designed to prevent exploitation of heap-based memory corruption vulnerabilities. And Android has gone through a bunch of different memory allocators in user space, from DL malloc very early on to give good performance, to JE malloc, and then since Android 11, since about 5 years, it moved to Scudo, where the goal was to have security first. Who knows Scudo as an allocator? Quick show of hands. Okay, about 2 or 5. Let me explain a bit the security primitives of Scudo. So Scudo is a secure allocator that ensures integrity properties by doing some kind of randomization, some kind of abstraction. And we looked at it and said, is it actually secure? Does it give us stronger properties than what JE malloc did before? And we found some troubling issues. Now, if you're trying to exploit the allocator, right here, the standard heap-based exploitation approach goes from the application. The application does a malloc on free, right? The allocator then allocates different parts of the heap space, allocates objects on the heap, and places them accordingly. We assume that the application has several vulnerabilities, such as overflows, use after free, and double free. And for heap-based memory allocator exploitation, we want to turn these overflows, use after free, and double frees into arbitrary reads and writes, because they are much more powerful, right? So we want to have a very strong primitive out of simple overflows on the heap. So the standard approach to do this is that using these vulnerabilities that exist in the app is to corrupt some inline metadata. Because the allocator, right, when you allocate the chunk of memory, it has some data at the end or at the beginning. And if you corrupt this metadata at both ends of the memory block, and the object is then freed, you can use the code of the allocator as a gadget to then turn this into an arbitrary read and write. And as all the connoisseurs of good literature will know, this is a very nice way for corrupting this allocator state that then allows you to leverage these primitives as part of your exploitation chain. So far so good, right? And we wondered if this is still possible for Scudo. Now, our threat model assumes that we can still corrupt heap memory. We can still corrupt the application is still buggy. And this is essentially what the Scudo should protect against, right? So how does Scudo work? Well, Scudo prevents attackers from arranging the heap in a particular layout. So when you do a couple of mallocs between one run and the next run, Scudo will shuffle the allocation, so it's not deterministic. To make sure that this actually works, right? If you allocate these 4 blocks, in the first run, the first block may be towards the end, then the second far at the end, third, fourth, and the order of the second run is very different. So each run is kind of different because of the seed for randomization is different, right? Scudo for this uses a randomization seed that is in the allocator itself, that is then used for shuffling. Okay? So this already gives you a very good primitive against exploitation. In addition to that, Scudo protects inline heap metadata by signing the metadata using a second key, right? So all the metadata is signed. And if there's an overflow, the signature no longer fits, right? And Scudo can terminate and abort the process. Are we good? Right? So this sounds like a very reasonable defense. So there's two mechanisms in there for Scudo that protect against exploitation. One, random shuffling, probabilistic shuffling of different memory blocks. And second, all the headers are signed to make sure that an attacker cannot compromise them. Now, this works really, really well on Linux, where you actually fork an exec VE. Because for each exec VE, you get a new randomization seed. Does this hold for Android? What's the Android execution model? Well, Android has a kind of weird particularity, right? And it's called the zygote process. Who has heard of the zygote process? Okay, another 5 people. Very good. So, Android needs to run on very crappy hardware and on very good hardware. To run on very crappy hardware, what do? Well, bringing up the whole runtime system to start and launch an app is incredibly expensive. You load about 500 libraries, you bring in a couple of 100 megabytes on your crappy little ARM device that is just dying and burning through the battery really, really quickly. So what does Android do? Right? It loads all the libraries into the runtime system, and then it pauses. And every time you launch an app, it just forks this process. Right? It just forks this zygote process. And then this means essentially that all the libraries, all the code, all the system stuff is already preloaded. Amazing feat for performance, right? Now, think about the two security requirements that we had before, right? When do you think the randomization seed and the key are being set? Right when you start the app. So the zygote forks and the evil app and the victim app will actually have the same ASLR layout. If you create a different app, right, this will have a different layout. Now, the Scudo secrets are also the same. So if you assume that an attacker has access to an evil app, they will know the ASLR layout, the Scudo secrets of the victim app, and can thereby easily compromise the other victim apps. And the victim app can be some app that is that holds some sensitive data, some sensitive information, or it can be a system service, because these are also Android apps, right? And now we can actually exploit bugs in these target systems and easily create arbitrary write primitives, because everything is shared. ASLR and Scudo secrets are shared, and this gives us a very nice primitive, and an attacker that has just access to this evil app here, which is a common assumption, can look at their own app and thereby use this for exploitation towards any other app. We front ported an old CVE to Android 14 in the binder in a system service, and that is now protected by Scudo. And then through IPC, we managed that our malicious app could exploit this target system by reusing the Scudo secrets that we learned from our own app. So this was a wood paper last year, and you can check out the source code and everything else in there as well. This was a Philip Mao, a student in my group. So Android user space security looks pretty bleak too. Well, there must be some light at the end of the tunnel, right? Let's see if we can get some nurturing some nutrition on the way. And we'll have a deeper look at the Android apps. And we explored Android apps in different depths. And if you've ever unpacked an Android app, you will quickly learn that there's hundreds of shared libraries in there. That is a bit weird, right? And these shared libraries are usually not updated. And one may wonder, what versions are these people using? Are they concerned about supply chain attacks? Are they concerned about different vulnerabilities that have been patched? Are they updating the library and libraries and taking care of them? So let's look into this a bit. So our goal was to assess the Android app ecosystem. And we had an amazing 5-step plan: download a bunch of APKs, build some binary similarity thingy to then do some binary matching, right? Machine learning sounds like an amazing tool for that, and we had either machine learning or some other thing in mind. Detect custom patches in Android native libraries to then point at different app developers and say, bad app developer, you're vulnerable. Bad vendors, bad. And then publish and profit, become rich, and look at good fortunes in the future. So this is ongoing work. We are still stuck at step 1. So maybe a bit later down the road we'll be able to work on the remaining parts. But I want to share some of the journey that we had for building our larger data set here. So our goal was to construct this data set for ground truth validation, and we just accidentally scraped some markets, resulting in a couple of terabytes of Android APKs. Don't sue us. We got 8.7 million APKs. Around 12% have native libraries that we grouped into around 1 million unique libraries. And by just scanning this large data set, we found some interesting statistics. A lot of code is actually shared. And we did the simplest thing, right? First, our assumption was that, hey, all these vendors, all these app developers, they're actually doing due diligence. They're going to download the libraries, the source code. They're going to compile it. They're going to update it. They're going to patch it. Everything is going to be unique, right? Because at least the app vendors, right? They are responsible, for the app. They need to protect their app against exploitation. They want to, for sure, they would like to patch any kind of security issues that are in there. Therefore, they likely download the source code, keep on track with upstream and whatnot. But unfortunately, what we actually discovered, the top 50 binaries account for 14.3% of all native libraries. And the top 5,000 binaries out of 1 million account for almost 80% of all native libraries that we find. That's a crazy number. Right? Just let this sink in, right? We have 5,000 binaries that account for 80% of all the shared libraries that are used across all the Android apps. Now, what's the security provenance for these binaries? Does this mean that they're just dumping, they're just wgetting or curling a bunch of files into their app repos and never updating them? You never know, right? Now, how do we infer the library names and versions? Because developers are, smoking crack. And the names, the file name can be anything, right? So the file name that you find in these APKs could be it doesn't even end in SO, right? It's a weird name that somebody likely renamed because they found funky or whatnot. But we need to find a way to infer library names and versions. So the obvious approach, given all the massive hype, is machine learning. Right, so we're going to use a machine learning tool to tell us what all the different libraries are. We're going to figure out which versions they are, what the custom patches are. And binary similarity is a solved thing. There's hundreds of papers in academia out there, right? So we can just reuse it, right? Who thinks machine learning is a great approach for this problem? Nobody? Who thinks it's a terrible approach? Okay. It's almost like Swiss voting. We have about 5% participation and 95% abstentions. So we looked at the machine learning tools. There's ASM2Vec, there's JTrans, there's hundreds of others. JTrans is one of the newest ones that has amazing accuracy. So we looked at this, right? And that's a pool size for the binaries, and it's much better than everything else. So it's comparing itself against like 8 other tools. Great, amazing, right? So it's still fairly reasonable, but we see that it kind of drops, right? And there's log 10 pool size. And remember the pool size for a bit. So what happens if we extrapolate this? So we did a very scientific estimation and extrapolated. And we wondered what is actually happening here, right? The issue that we're facing is that training these models is incredibly expensive. Machine learning works great for small data set, but breaks for large data set. On the data set of 350 binaries that was used in the papers, it takes around 12 hours to create the embeddings and do the actual training. Our data set has 1 million libraries. So it would take reasonable 40 years to actually do the training. And the question about accuracy will remain open. So the existing machine learning tools, they scale, like if I want to give you a bit of a mental image, they scale a bit to pools like this, like a pool size of different libraries that looks a bit like this, 1,000 liters. But we are facing 10 Olympic pools with like 28 million liters of water. So it's a bit of a slight difference in scope. So machine learning clearly doesn't scale to these kind of targets. So very sadly, we had to resort to other alternatives. The clustering based on hashes already helps some, but we also looked at just some of the library statistics, and we wondered like how many of those libraries are actually copy pasted, and we see that there's a bunch of libraries out there that is fairly zoomed in because there's an incredibly long tail where people actually do use custom libraries, but some libraries are used across thousands of apps. And the steps indicate somewhat that some developers download the same tarballs, right? They just download the same tarballs and they never update them. We started exploring where these tarballs came from, and we found that the majority of libraries actually are just downloaded from Maven, a source that keeps on giving. Looking at just Maven, we match around 30% of libraries, using some heuristics for React Native, to disambiguate that, because React Native, did some funky stuff on the hashing and on how they upload it. We get to around 60%. So based on simple heuristics, we actually get to around 60% of libraries, and we don't need any AI or machine learning at all. So we now know the provenance of around 60% of libraries, and when we looked at some of the libraries, we kind of, were a bit worried, especially about the lack of patches to these libraries. Who remembers droids on roids? 1. Droids on roids, anyone? Okay, so 2 or 3. So this was a very well-known vulnerability about 6 years ago, right? So it's a double-free memory corruption bug that was in the WhatsApp code itself through the droids and roids library when opening a GIF image that you could then exploit. Now, we looked at this droids and roids library that is still fairly popularly used. There's 45,000 Android apps that still use this library. Right? So this vulnerability is 6 years old. How many apps remain vulnerable? Well, about 78% of apps remain vulnerable today. If we filter to only apps in the Play Store, it's still around 60%. Or around 3,000 apps that are still in the Play Store. So which means that, well, developers don't update their libraries. They just download a random library, drop it into their repository, and think they're good to go. Now we're looking at the top 3 apps vulnerable to the CVE. There's the screen recorder, which has only 143 million downloads. There's Paint by Number, a coloring game, where you can share this to your, send these images to your friends. Only 242 million downloads. And there's the Update News for Samsung with 400 million downloads. Right? So this is crazy that these vulnerable libraries still exist and the app developers just don't patch their code. Now, what we did here is there's a caveat, right? We only showed that the app, that the library was present, that it was used, loaded, but we didn't check the actual data flow, so we didn't exploit the target app. But maybe that's a call for the community to look at some of these nice libraries and go play with all the bug bounty programs that are out there. Because these are some very, very easy, low-hanging fruit that with a couple of hours per app, you can have a nice end-to-end exploit. That brings me towards the end of the journey. I want to highlight some of the aspects that I presented today. This is not just my work. Obviously, this is work of my research group that I presented. These students are doing all the hard work. They're spending all the time in the lab, pushing really, really hard on their research projects. Where the Hacks Hive research group, we're doing a lot of software testing, where the goal is to get rid of as many bugs as possible to help developers. We're also doing some mitigation as a last line of defense, and compartmentalization to break these large and complex applications into smaller fault domains. If this talk was interesting, you can join us on our research journey. We're here at EPFL. We're doing lots of fun stuff. The students are doing the hard work, while I usually head to the nearby mountains to ski. So yeah, Android security remains an elusive target. Right? The Android ecosystem is incredibly complex. Well, there's a couple of good things, right? They've got per app compartmentalization down fairly well. Like the per app compartmentalization is a great improvement for security. The app model is really, really good. Sensitive data remains in the trusted world. So the idea of having a trusted world and separate this is pretty well thought out as well. Very good. Now, we can talk about how many apps should be in the trusted world. And I would argue that we don't need all the AI crap that the current vendors are pushing in there. This should be restricted to sensitive data like fingerprints, keys, and whatnot. What was expected to some extent, because it's just not a piece of software, is bugs in the hypervisor, like the secure monitor. This is pretty sad, but unfortunately expected. What's unnecessary are the vulnerable communication APIs when sending data back and forth. And as discussed, we worked with the vendors to actually make sure that this can be updated and made better. Terrible is forgetting rollback. So the vendors of these devices should actually work on reasonable rollback and ensure that, hey, as soon as a trusted application is patched, it can no longer be abused by an attacker. Naive, that's unsafe allocators that create new attack surfaces. Unfortunately, Scudo is less secure than the other allocators that were used before in this execution context. So even if the allocator is secure by design, you need to evaluate the security constraints in the runtime environment that you're actually using. Right? So this may completely invalidate some of the assumptions you had. And the crazy part is just reusing some of these apps without any updates. So there's lots of opportunities for you researchers out there to find issues across all the different layers of the software stack. And Android remains an amazing opportunity and fun target. Thank you very much. I'm happy to answer any questions you might have. Yes, please. I guess I'm using this microphone here. 1, 2.
Hey, thanks for the great talk. So I have actually 2 questions. First is, so we have the Scudo allocator, and you said that, there's the zygote process that forks, and the randomization key for the for this something is like the same, right? My question is, because there are devices with memory tagging extensions, does this help anyhow?
MTE helps a bit. What you can use is the tags for all the memory that has already been allocated. You don't know the details for anything that's
so basically you don't really have to attack the app. You can attack the libraries that are loaded, and
yes.
And you still have this
you still have enough
leak for free,
and you have a couple of 100 megabytes of allocated data to explore, right?
Yeah. My second question is about the TE stuff and those rollback vulnerabilities, because if I understand correctly, this mechanism for rollback versioning or whatever, it has to be just implemented once, right? Or does it have to be done per app?
So the runtime system needs to keep track of the rollback counters, and the runtime system, like the
by runtime system, do you mean the secure monitor, or
either the secure monitor or the OS on the trust zone environment in the secure
so
world?
How the hell is that an issue? I mean, it's really like surprising that it isn't just implemented once.
The thing is, it's really a great question, right? Why do vendors not implement rollback correctly? There's 2 approaches. The Google approach.
Why isn't this open source? Or maybe it is.
Part of this is open source, but the Google approach is, they say we don't use rollback counters at all, because this would potentially prohibit you to go back to earlier firmwares. Like Google wants you to be able, Google wants you to flash earlier firmware. So their solution is that you can only load trusted application from the system partition, which is read-only, which is assumed that the attacker does not have access to. Right? So that's one solution where you don't need rollback counters, where it's just secured in itself because it's read-only, right? The attacker cannot...
you just cannot install your own.
You just cannot install your own. You have to
install the new firmware of the whole ROM, right?
Correct. And then it's already game over. If the attacker can flash your system, it's already done. So that's the Google approach where you don't need rollback counters. In the other systems, you need to have a way to potentially support downgrades for an older firmware version or keep track of the rollback counters. And Samsung is starting to roll out better rollback counter mechanisms on their phones, but they're struggling with their mode of operation is that each phone has a different team, and the teams don't talk to each other. And when they start a new phone, they fork the code base, and then the code base develops individually on the teams, which is a very interesting way to develop code, but.
Yeah, but so to sum up, we should probably use the latest possible flagship phones because they are probably mostly updated with all of this. But at the same time, we still have this bug with Scudo and even with memory tagging extension.
And for secure monitor, I'm sure there's more bugs. Like we fussed for a couple of weeks, I'm sure there's more bugs. The attack surface is so broad on the secure monitor. So for any of you who's interested. Other questions?
First of all, thank you for the great big question about the communication API. Do we know why they did the param type check optional? Was it some kind of premature optimization because it would cost too much every call, or what was the consideration there? Do we know?
Excuse me. I have no idea. Sorry. Again, it's I wouldn't have designed it this way, but you know, it's a consortium, and usually if you end up with a couple of thousand pages specification, it's like death by many parties.
Also, thanks for the great talk. One question about Scudo and its seed. Would it be possible to reseed Scudo after splitting a new process from Zygote? And if not, why not?
It would not be possible because all the existing heap objects that have already been allocated would have to be kind of re-encoded. Right, so this would take quite a bit of time. The only safe option is to execve. And this is what Graphene OS actually does. So if you're using Graphene, which is a secure version of Android, they actually don't use Zygote because it's much more secure. Right? So they don't use Zygote to preload everything, but they actually fork an execve whenever you start and launch an app, which gives you a new ASLR space, gives you new Scudo secrets, and is a much safer option.
So I think we potentially have time for one more question. I see one over there.
Thank you for the talk. Just a small question when we come back to business context, if I may say it this way. Maybe you've heard, I'm sure you've heard about Microsoft Intune, for example, for Android and such. Just wondering, I'm not a mobile expert at all. Just wondering how this containerization that they do, you know, this split between normal apps that you can download from the Play Store and these work apps. How does this get placed regarding to the architecture that you presented? You know, there is this public space, this trusted application. How does this take place? And do you think, at some extent, that this is a good way to do it?
Good question. So the ARM model allows you to separate between different worlds. There's the normal world, there's the secure world. And the idea is that the secure world gives you an opportunity to have like highly sensitive data. The original intention was to have a few small apps that require additional protection. So in the normal world, you'll be running Linux or a Linux kernel and then some userland, such as the Android userland. And in the secure world, you're running like a small operating system to then launch the trusted applications that take care of all the small little details, handling your private keys and whatnot. So even if the normal world is fully compromised using either like a compromised app or even compromising the kernel, you cannot compromise your private data. So you could not leak your fingerprint information, right? Mm-hmm. Does that answer the question?
Somehow, yeah. Thank you.
Cool. Thanks.
All right, thank you. So maybe we can just give another round of applause for Mathias.
Thank you.